Okay, now let's start something which is towards releasing the constraints that I placed. So earlier it was the same search kind of a modeling. So my assumption was everything is deterministic in nature. Now I'll add in a little element of stochasticity or a little element of probability or a little element of chance or a little element of luck. And of course, in games, even as simple as these, there are two things which happen in numerous games around. The first is you take a coin and you toss, and the toss of a coin decides what will happen next. The other, of course, is a dice. So you take a dice, you roll it along. If you get one, you get to make one move. If you get two, you get to make two moves, and so on and so forth. So the moment I add this luck, the moment I add this chance, one thing changes, and that is my classic two-player game, you and me, human and computer, is now a three-player game. Human, you, computer, me, and God. God is the third player, and God is playing what happens, whether you get one, whether you get two, whether you get six. So many times you need a six. God is a bad player, doesn't give that to you easily. So let's model this thing up. So of course now there will be three players, and my players will be the max, which will try to maximize the utility value, min, which will try to minimize the utility value, and the third player, God is not a good name, so let's call it as chance. So max nodes, min node, and chance nodes, these together make in stochastic games. So we're into stochastic games. We looked at max and min. Let us say how God works. So max was this, min was this. So let's keep a representation for the chance node itself. Remember, circle used to be the state. Now I know I'll not be drawing state. So circle is for the chance nodes. And that's exactly what happens. So at a particular state, I haven't drawn it up. The chance nodes can have multiple options, either a head or a tail, or let's say a roll of a dice. So 1, 2, 3, 4, 5, 6. And again, let me assume that the true utility values are 2, 3, minus 1, 2, 0, 0. So now which action does God select? Now it turns out you select best according to you, I select best according to me, chance or God selects the ones which are random. So the probability of this is 1 by 6, 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 the probability of this is 1 by 6. Now I do not know which one of these will get selected. So like last time, there's no direct answer that this is the path or this will be the path. I don't have a direct answer, but what I'll try to do is mathematics primer. There are 6 branches. One of them will be randomly selected. So I calculate the expected value, and all decision making will be to maximize the expected value. So let's see what's my expectation around from this node. Of course, it is 1/6 chance I get a return of 2, 1/6 chance I get a return of 3, 1/6 chance I get a return of -1, 1/6 chance I get a return of 0, 1/6 chance I get a return of 0, and 1/6 chance I get a return of a 0. So that's 2 plus 3, 5, 6, 7 minus 1, that's a 6 on 6 or 1. So my expected returns from this is 1. It doesn't mean you will get 1. In fact, you can never get 1. You will either get 2, 3, minus 1, 2, 0 or a 0. You'll never get 1, that's for sure. 1 doesn't exist. God will select one of the branch, but God cannot magically give you 1. So this one, of course, by mathematics means that if the game is played infinite times and the returns of all the infinite times are averaged out, the average return will be a 1. That's all that it means. So again, I really cannot take a game and solve the game tree using these chance nodes. So let's again go to the same tic-tac-toe. This time let's make it even smaller. This time let's make it 1 cross 2. And all that I do is you first have a toss of a coin. Head, Max gets to move. Tail, Min gets to move. So let's do that. First, God makes a move, a head or a tail. So these are the choices. Head, Max gets to move with a probability of 0.5. Tail, Min gets to move with a probability of 0.5. Then, of course, it's a 1 cross 2. So Max could either put a X blank or Max could put a blank X as the two state, but whatever happens, then a chance node is activated around over here. Again, it could be a head or a tail. Head with a 0.5 probability, tail with a 0.5 probability. Head, Max gets to move, tail, Min gets to move. If Max moves, it has only one option that gives it a cross. If Min gets to move, there's only one option that Min has, so there's only one blank. So the returns are, of course, a +1 and a 0. On the other hand, over here, again, it could be a 0.5 probability, a 0.5 probability. So with 0.5 probability, Max gets to move. If Max gets to move, it's a -x, so it becomes XX. Min gets to move, so it's -x. Min places itself first. So the returns are, of course, a +1 or a 0. And similarly, you will have exactly the same branch, which is around over here. So I could virtually copy that around over here. So in this case, what happens is Min has won the toss. So Min gets to move. So a chance node, a head, Max gets to move. I'm talking about the two options with Min, which give in a nut dash, a dash and a nut. So here Max gets to move, and if Max gets to move, it puts a OX. Here Min gets to move, it puts a OO. Here again a toss of a coin, head with a probability of 0.5. Max gets to move, it puts X over here, so it becomes XX. Min moves, it gets to put O over here, OX. So the returns are 0, 0, -1. Oh, Min was playing this. Why did Min play for Max? Bad Min. Min was playing it. So let me correct that up quickly. Oh God, who will do that? Got the chance by a toss, completely fair, played by God, and instead of marking its own piece, marked it for the opponent, worst player. So 0 and of course a -1, so that's 0 and this is a -1. So that's what my game looks like. Max, of course, will, I mean, I did not go strictly backtracking, my bad. I should have done. So 0.5 times 1, 0.5 times 0, so it becomes 0.5. Now I'll try to go in a strict backtracking way. So that's a plus 1, that's a 0. 0.5 times plus 1, 0.5 times 0, so that's 0.5. Maximum of 0.5, 0.5, 0.5. I'm strictly going backtracking, so 0 minus 1, 0.5 times 0, 0.5 times minus 1, minus 0.5, 0, minus 1, 0.5 times 0, 0.5 times minus 1, that's a minus 0.5, minimum of minus 0.5, minus 0.5, minus 0.5, 0.5 times 0.5 plus, so this was a 0.5 of course, plus 0.5 times minus 0.5, that's 0, and that looks like a better game, so everybody has equal chance of winning, nobody is getting favored unlike the last example. So a quick example of a stochastic game, the only thing we modeled new was these nodes which are called as the chance nodes. So I don't know what will really happen. God could decide this branch, but then definitely men will decide the branch which is best for itself. Both of them are equal. So let's say this. God, it's up to God what happens. So, but then men will play it again and men will win. It's a bad game. Every major action is being decided by God. The humans are not doing anything. So all the major decisions are happening at the chance node level. But yeah, I mean, that's a stochastic game. Now what we'll do is we'll study some more interesting things. So first, let's say a multiplayer game. So if you can do it for 1, if you can do it for 2, can you do it for multiple using exactly the same principles? Now, multiplayer games will not be zero sum. There will be a score to A, there will be a score to B, there will be a score to C. Yes, they could be zero sum. So each one of them will get a score and each one of them will try to maximize their own score. So there's nothing like max and min. Let's call the players as usual A, B, and C, and let's keep 3 players only, and let all of them be denoted by the same sign. So let's play a game, synthetic. So first A plays, then B plays, then C plays, then you get a cut off. So now there'll be 3 scores, 1 for A, 1 for B, 1 for C. So let's write down A gets 3, B gets 0, C gets a minus 2, A gets 2, B gets 1, C gets a minus 1, A gets 3, B gets 2, C gets 1. Everybody wins. I like this game. So similarly around over here, in this case, there are only 2 actual there are only 2 branches possible. So it's a minus 1, 0, 1. It's a 2, 0, 3. And similarly for the rest of them, so that's B, that's C, and the options possible are the playoffs possible. Again, I've not got strictly backtracking. I should have gone 2 minus 1 minus 1, 0 minus 1, 2, 3, 1 minus 2, and minus 2, 1, 3. So my notations, of course, not written is these are the returns for A, these are the returns for B, and these are the returns for C. So if you are C, you take this action, you get a minus 1. You take this action, you get a minus 1. You take this action, you get a 1, which is the best. This one is clearly the best. So C will definitely take this action, and it will be a 3 to 1. Similarly here, take this action, C gets 1. Take this action, C gets 3, which is better. This is better for C. So it's 2, 0, 3. Now think like B. You take this action, you get a 2. You take this action, you get a 0. Which one is better? You want a 2. This is clearly better. So it's 3 to 1. Go here, C. You either get a minus 1 or you get a 2. 2 is clearly better. So it's 0, minus 1, 2. Think like C, you get a minus 2 or 3, 3 is clearly better, so it's minus 2, 1, 3. Now it's not like maximizing, minimizing different, everybody is maximizing their own self. B will either get a -1 or a 3. So let me underline these things, the B's decision making. So B will either get a -1 or B will get a 3. B will either get a -1 or it will get 1. I think B will prefer 1. If I was B, I would have preferred 1. So it's -2, 1, 3. And think like A. So do I prefer a 3 or I prefer a -2? Definitely I prefer a 3. So it's 3 to 1. So A will first choose this, then B will choose this, and then C will choose this. Everybody is maximizing their own returns. In fact, this happened to be a good example accidentally. Everybody is getting good returns. Now, this is theoretical. It's theoretical because your modeling is A thinks B and C are enemies. They are just maximizing their own terms. B thinks A and C are enemies. They are maximizing their own terms. And similarly with the other one. What really happens in multiplayer games is that A is a wonderful young little boy. B is a person whom A owed some money and B did not return. And C is allegedly, nobody has confirmed it, the girlfriend of A. So what happens is A and C will play together as a team. A and C will say, let's play as a team. Whatever returns come, we'll in reality share it. So if we win $1 million, it's an example, I could say any goddamn amount, finally we'll share it. So, and then B is alone. So this is reality. This is the theory by which we modeled, and this is reality. A and C are playing as a team to kill B. Once B is virtually outside the game, then A and C have a breakup. Now A and C are enemies. They are trying to maximize what is best for themselves. That is how it goes. So if you watched all those dramas of the Indian television, Big Brother, Big Boss, or you watched in the so-called reality shows, or in fact even in live sports, does every team play to win? No, some teams make other opponents win to get a stronger team outside the series. It's practical, it happens. So, do all the players in reality TV show play for themselves? No, sometimes you lose to get a weaker player in, to get a stronger player out. It's all a part of the game. This game is called as an alliance. Now, the problem with alliances is, it happens by a lot of factors which computers don't know. So, computer doesn't know who will be easy to please, who will be easy to brainwash, who will be easy to have a charm around, who has an infatuation on you. Computers just don't know that. So, they cannot form alliances. They cannot tell a person, okay, I'll give you some money, just help me out a little. That's also how non-zero-sum game, two players will be made, but then again exactly the same problem that arises over there as well, that yes, every player tries to maximize it for the score for himself, but if you play like that, you may not end up in something which is mutually beneficial for both of you. Even in two-player game, where you don't have the C rest, everything remains exactly the same, and A tries to maximize on A values and B tries to maximize on B values. What really would happen is that A will talk to B with this giant game tree, and A will tell B, see, let's play it together. If you follow this route, which is best for you, you will get so much. On the other hand, if you follow this route, you'll get a little bit less, but I'll pay you. I'll give you the money, I'll give you the fame. Now, it's an unwritten bond. A may still cheat, people do cheat. It's an unwritten bond, but that happens in real life. So even for two-player game, you've got all these issues which come into play, and that's why we said that we'll only deal with, in principality, the zero-sum game where you cannot do this. If A goes to B, promises something, then and A wins, then B is definitely losing. So it's a zero-sum game. That's why zero-sum games are actually which are pretty interesting, and all these issues are absent. How does AI deal with all this? Now you're talking about trust. A promised something, did not do. You're talking trust, and machines won't make those kinds of decisions. In fact, there's no way you could model in the trust factor like these. And hence you have in AI, we do not model all those things as well. Two-player zero-sum, the best thing. No alliances possible, no trust issues, nothing at all. So, the last topic of the day that I will touch upon extremely briefly is the partially observable games. The typical example is a card game. You know you have a 5 of hearts with you. You know you have a 3 of spades with you, and what else? You are playing. So that's a table, and you are playing against the opponent, and you absolutely do not know. And these are practical games. So now what you need to do is that because you do not know what the opponent has, you need to take all probabilities. So you say the opponent has 3 of spades, it cannot have, it's only with you, 3 of hearts, it has 5 of hearts, it has 1 of hearts. This is the probability, and similarly all the other options. This specifically is called as the belief So you cannot observe it, you cannot see it, you cannot model it, you cannot know it unless you cheat. But you have some belief inside, and this belief is probabilistic, and then you decide if this is the thing, then I play like that, these are the expected returns, this is the returns, these are the expected returns, these are the expected return. You do the same expectations, and then you calculate what is the best move which is possible, which holds on to be the best under the assumptions that you have laid down around over here. So now you're talking about, because you do not know what the other agent is having, you have absolutely no idea about the other agent. So you make a belief of the other agent, the belief is probabilistic, you assume all possible source state, you assume all possible start state, you assume everything. These will change with time as well. So once the opponent makes a move, your belief for a certain things will increase, your belief for a certain things will decrease. But then at every time you'll have a probability distribution which says what sequence is the opponent most likely to have. Based on that, you calculate all the expectation values. The funny thing, last time I gave in at least 4 questions on belief states for a completely different thing. Those questions are still unanswered. So I'm becoming a little bit more inquisitive about giving questions on belief states, not only on this, but as well as on search. So today, to end it up, to sum it up, we talked about adversarial agents. We talked about agents where somebody is acting contradictory to you, and we did exactly the same thing like you do in a game of chess. Practically by pruning in quite a lot, pruning branches, alpha, beta pruning, cut off, all the types of pruning which is possible, and then by forward thinking, you make a guess about which is the best move possible. The most important part was, of course, how to make the guess function, how to make the heuristic function, how to guess the values. Usually in labs, when they are questioned, I give you one. Practically, that's the only thing which is possible, which is important in AI. How do you make good heuristic functions, and which is a course in itself. But what we've done is that we've learned how to do decision making under such adversarial condition wherein the player in front of you is outsmarting you and you are outsmarting, and you consider all combinations of options in order to arrive what is best for yourself, which of course mean what is the worst for your opponent. And of course we do end up the lecture with this. Thank you.